This video covers Lesson 5-2 for Secondary 1 Math, Scatter Plots. Warm-up 5-2. Answer the following questions from Lesson 5-1, page 232. Number 1. A pattern of behavior usually observed over time is referred to as a blank. Well, it is referred to as a trend. Number 2. A negative correlation occurs when the x value increases and the y value decreases. Number 3. A scatter plot shows the relationship between two sets of data on a graph. Number 4. If a relationship does not exist between two sets of data, then the relationship is said to have no correlation. Number 5. A line drawn on a scatter plot that describes the trend is called the trend line or the line of best fit. Number 6. Which scatter plot has a stronger correlation? Well, we would say that the scatter plot A has a stronger correlation. That's this one here. And the reason this one shows a stronger correlation is because these points are a lot closer to that trend line. If we look over at B, you'll notice they're further away, from the trend line. And so a stronger correlation is in A. So again, the scatter plot A has a stronger correlation because the points are closer to the trend line. Number 7. Is the relationship in number 6 linear or exponential? And how do you know? So first we got to decide, does this look linear or exponential? So remember your exponential curve goes something like this. Linear is a straight line. So looking above, we're going to look at the trend line. And notice our trend line in the two above is linear. That is a straight line, so it would be linear. So we'll say it's linear because the trend line is straight. The other reason we can identify number 6 as a linear relationship is because if we were to take our pencil and place it on top of as many points as possible, it would cover almost all of them, and it would follow that pattern. And our pencils are straight, and so we have a linear relationship. Now, if I were to try to cover them, but missing some and making it see a bend in our scatter plot, then we would have an exponential relationship.
Okay, so lesson 5-2. Here we're going to start out by using the following table that shows a relationship between a vehicle's weight and its gas mileage. And we're going to graph that following data on the coordinate plane, and we're going to label the x-axis and the y-axis. So in our table, this first one right here, the weight, is going to be our x value. The gas mileage is going to be our y value. So when we go down to our graph, we're going to label down here on the x-axis, we're going to label it weight. And we're going to do that in pounds because that's the units that they're using for the weight. Then we're going to come back and look at this, and we have mileage, gas mileage, or MPG. That's going to be our y-axis. So we're going to go gas mileage, or MPG, miles per gallon. That's how we're going to measure that. And then next, we're just going to be plotting these points. So the first point here is the 2,100 in pounds and 36 miles per gallon. So 2,100 is going to be halfway in the middle of this box right here. I'm going to have to go up to 36. So our first point would be here. I'm going to do the same thing on the next one, 2,300, 36.5. So 2,300 will be in the middle of the next box. We're going to go up to 36.5, so about here. And then do your best to graph the rest of these. We've graphed the first two. So go ahead, pause the video now and graph these. So pause the video. now that you've finished this scatter plot, it should look something like this one on the screen. We got our labels. We see these points. We had to estimate a little bit on these points, a few of them, so they could be slightly different on your paper. But looking at this, we're trying to find out what kind of correlation does this scatter plot have. And as we look at it, we'll notice that as we go from left to right, we're going down. These points are mostly going down. And so this means that we have a negative correlation, because as we go from left to right, the points are going down. Now, if we think back to our warm-up, we can also see how we can finish this next statement that states, as the weight of the vehicle increases, the gas mileage decreases. And it's decreasing because it is going to be a negative slope, right, or a negative correlation. And so, decreases. Now, we're going to draw our line of best fit, and we just got to do our best with this. Remember, you take your straight edge, you're going to line up the best you can through those points. Make sure that you're following the trend of these points. You might have a couple that are a little further away from the line, and that's fine. So go ahead, pause the video, use your straight edge, and draw a line of best fit. Okay, so now that we have our line of best fit, or what we think our line of best fit is, we're going to go ahead and we're going to pick 2 points on this line of best fit. Now we want to choose these 2 points that are easy for us to identify their values. And so when I look at these 2 points, I'm focusing on where the line crosses the corner of squares. And you can see down in the bottom right, this one crossed nicely, so that's going to be one of my 2 points. As I go up, my lines are not perfect, okay? I don't have a straight line tool, but my next one is going to be this point here that I just marked. And so I just need to find the x and y value of each point, and then I'm going to write it to the left of my graph. And so this left point here, I notice it's between the 2,800 and the 3,200, so that's at the 3,000 mark, so this is 3,000. And I go up and that's 31. Okay, and then the next one, as I look through this, I go down here to this other point. This is going to be 3,800 pounds and 26 miles per gallon. So I'm just going to transfer these 2 ordered pairs over to the left side of my graph. So I have the 3,000, that's a 0, 31, and then I have the 3,800, which is 26. Now our goal is to find the slope and write the equation of this line of best fit. And so we're going to take and we're going to find the slope by finding the change in y. So 31 to 26, which is a negative 5. We got to subtract 5 there. And then a change in x, 3,000 to 3,800, is going to be a change of 800. Now we're adding that, so it's positive. Now we're going to write it as a fraction, the change in y over the change in x. So negative 5 over 800, which if we put that in our calculators, we'll get a decimal. And we're going to round that to nearest thousandths, just because down here it says round the nearest thousandths for slope. Okay, and that's going to be a negative 0.006. So negative 0.006. Now that we have the slope and we have a point, we're just going to pick one of the points. And I'm going to choose the 3,031 point to substitute into y minus y sub 1 equals m times x minus x sub 1. And so we'll get y minus 31, that's the y value in our point, equals our slope, which is negative 0.006 times x minus 3,000, our x value from the point. Next, we're going to distribute. So we're going to distribute our negative 0.006, which means that we have y minus 31, because it hasn't changed, equals negative 0.006 x's plus 18. So next, we're going to add 31 to both sides of our equation. And we get y is equal to negative 0.006 x's plus 49. So there's our equation for this line of best fit. Now you might be wondering, hey, wait, why is the y-intercept 49? I'm looking up here and it's hitting 37. Well, that's because this is not the x-axis, or the y-axis, over here on the y side. Because the y-axis has an x value of 0, but we're at 2,000. And that's why we don't see the actual y-intercept on this graph, because of the window we're looking at. Now, we do want to write a sentence in number 6 explaining what the slope represents. And thinking about our slope, we have to consider a couple things. The slope is this number right here. And we have to consider that this is a ratio. It's this negative 0.006 over 1. And if we use units, that's going to be miles per gallon over pound. So what this means is that the gas mileage, or the miles per gallon that a car gets, is going to decrease by 6/10,000ths of a mile per gallon for every 1 pound. So we can say in words what the slope represents is that the gas mileage decreases 0.006 miles per gallon for every additional pound it weighs. Okay, so now we're going to turn the page and we're going to talk about the correlation coefficient, which they use the letter R to represent this correlation. Okay, it's a number that assesses the strength of a linear relationship between two sets of data. So it's just telling us how strong or weak that correlation is between those two things. So let's take a look at what the correlation coefficient looks like and what it means. So a correlation coefficient is going to range from -1 to 1. So we have this range of numbers from -1, if you think a number line, right, all the way over to 1. We'll have 0 right in the middle, okay? And when we see these, if we see a -1, that indicates that we have a very strong negative correlation, okay? And if we see a +1, it's going to be a positive, strong correlation, okay? 0 indicates that it's very, very weak, or basically that there's no linear correlation at all. And typically when we see a scatter plot like this, the points are all over the place. There's no pattern to it. We can't reason as to what this would look like and what's happening. But sometimes people refer to the 1 and the -1 as a perfect correlation. Okay, meaning that every data point that we have, or data point that we have, is on that line of best fit. This is very rare, and we don't really see it. Okay, but we're going to see a lot of these other possibilities. And here's how this is broken down. So if we see a value of R between 0.8 and 1, we're going to say that it is a strong positive correlation. When we venture away from this and we go between 0.5 and 0.8, that's more of a moderately positive correlation. And then we get to 0 to 0.5, and we say that's a weak positive correlation because the values are still positive. But it's very little. The correlation is not as strong. It's closer to 0. Likewise, when we look at the negatives, so -0.8 to -1, it's going to be a strong negative correlation. And when we have -0.5 to -0.8, that's a moderate negative correlation. And then our last one, the 0 to -0.5, is the weak negative correlation. So you see that the sign of R is actually telling us if it's negative or positive, and the value is telling us if it's strong, moderate, or weak in its correlation. So how do we find the line of best fit and the correlation coefficient R? Well, it's tough by hand, as we've talked about before, but we can use the Desmos.com calculator again to help us find the line of best fit and the correlation coefficient. And so I'm going to switch my screen here. You could see what we're going to see here by looking at our paper, but I'm going to switch over to the Desmos.com calculator and walk you through the steps in finding the line of best fit and the correlation coefficient. Okay, so here's our Desmos calculator, okay, Desmos.com calculator. And what we're going to do is we're going to enter the information from that table of weights of cars and their gas mileage into a table. So we got to create that table by clicking this plus sign, and then clicking table. So here it is. And we're just going to enter the information from the table on our paper into Desmos calculator. All right, so that first one was the 2100 and the Y value was 36. And so I'm just going to hit tab, keep moving down my table and enter the information. I'm going to go ahead and pause the video and do it yourself. Okay, so now that you've got that information in your table, the next thing we're going to do is we're going to go over to this wrench in the top right corner. We're going to click on that and we're going to change our window. And remember, we want to use the smallest x value and go a little bit less, the largest x value and go a little bit more, and then do the same thing with our y values for the y-axis. So looking at our x values in our table, I'm noticing that the smallest x value is going to be the 2100. So I'm going to go down to about 1500 to give myself a little bit more space to kind of see what's going on. Now, the larger side is up to 4,000, so I'm going to go 4,500. So I'm going about 500 extra, keeping my numbers easier to identify, okay? Then I'm going to go down to my y-axis here, and you can see my graph's already changing. And my lowest y value is going to be 24. So I'm going to go a little less, go like 15. I'm going to go to my larger y value, and I see that the largest one is 36.5. And so since it's 36.5, I'm going to go a little bit more than that. Maybe shoot around, I don't know, 50, 55, okay? And then you'll see that again on your page. You see it as a picture, okay? But looking at it, it looks something like this. And to be honest, it kind of looks like it kind of bends, right? It's looping, yeah, bending down and then bending back to horizontal. But we have to think about this. Is this exponential or is this going to be linear before we can decide what kind of equation to put in? And so as I'm looking at this, I notice that they're kind of along the same line. Yeah, there's some variance, but it's a scatter plot. And that's how scatter plots work. Okay, so I'm going to go with the linear here. And to come up with our equation and our information about our correlation coefficient, what we're going to need to do is we're going to go ahead and type in y, and then we're going to use that similarity sign. It's the top left spot on your keyboard. You go shift, right? And you got it right there. Then oh shoot, I forgot. Let me correct myself for just a second. We got y, and then we got to type this 1 for subnotation, okay? Then we're going to do the similarity sign, and then we're going to go m, and then we got to go x, and that 1 again, just hit that 1. It automatically does the subnotation. You don't have to worry about it. Then we got to go plus, and we got to put in a b because we need a y-intercept. And there it is. There is our line of best fit. And you can see how close those points are to it, which helps us identify that, yeah, this is definitely linear, right? It's not like bending and turning like an exponential. And so here we go. Right here in the bottom left, you'll see it. We've got our information. Here's our slope. Here's our y-intercept and our correlation coefficient.
Now that we've used the Desmos.com calculator to help us identify the correlation coefficient, the slope, and the y-intercept, which we found here, and I've copied over in this picture, we're going to write these down and write the equation for the line of best fit. And we're going to round the slope to the nearest thousandth. And so the thousandths place is the 6 in our slope down here. So we look next to that, the 10,000th spot, which is a 9, tells us to round it up. And so we're going to round our slope to negative 0.007. Now for the y-intercept, we're going to round to the nearest whole number. And so we're just looking at that first decimal spot, which is an 8. That's going to tell us to round this up. And so we're going to get 52 for our y-intercept. Now writing our equation, we're going to put it into slope-intercept form, which is y equals our slope, in our case is negative 0.007, times x plus the y-intercept of 52. And so this will be our equation for the line of best fit. Now the other thing that our Desmos.com calculator helped us with is it helped us identify our correlation coefficient, which is here. And we're going to round this to the nearest hundredth as we write it. And the nearest hundredth is this 2 spot. The 3 tells us to keep it the same. And so we're going to say that our correlation coefficient is negative 0.92. And this correlation is telling us how strong the relationship, this type of relationship, is between the two factors, meaning the weight of the car and its gas mileage. And it says that this is a strong correlation because this number is close to the -1 or +1. In this case, it's close to the -1, and it's negative, right? And so it's a strong negative correlation. That doesn't mean causation. It doesn't mean one causes the other, but there's a strong relationship with these two elements. Okay, so we're going to use that equation that we just wrote on the last page. Okay, and that equation was y equals negative 0.007x's plus 52. And we're going to use this as we answer 11 and 12. Because in number 11, it says, using the equation from number 12, predict what the MPG would be for a vehicle that weighs 5,500 pounds. Now it says for number 12, I apologize for that. That should not be number 12. If you look back at your notes, that's number 8, okay? So we're talking about number 8 here. But we're going to use that equation, and we're just going to substitute in the weight, and the weight was the x value. So when we substitute in, we would get y equals negative 0.007 times the 5,500 pounds plus 52. And that's going to tell us the gas mileage of a car that weighs this much weight. So take a second, pause the video, put it in your calculator, and see what you get. After putting in your calculator, you should get that y is equal to 13.5 miles per gallon. Not the greatest, but hey, you know, that's what happens sometimes when you get really heavy cars. Number 12, using the equation from number 8, we're going to predict what the miles per gallon would be for a vehicle that weighs 1,200 pounds. So a lighter vehicle. Again, we're going to substitute in the weight for x, so we'll have the equation y equals negative 0.007 times 1,200, and then we're going to add 52. Then typing that into your calculator and hitting enter, we would get 43.6 miles per gallon. Now we're going to go ahead and look at number 13. What does the y-intercept represent? Well, to understand this, we first have to remember what the y-intercept is. The y-intercept is a point, and it's 0 for the x value and 52 for the y value. And the x value, remember, is the weight of the car. The y is the miles per gallon it will get. So we can say a vehicle that weighs 0 pounds would get 52 miles per gallon, which doesn't really make sense because cars are not, or any vehicle is not going to weigh 0 pounds. And so, not really helpful, but that's what it means. On number 14, we're going to ask the question, does this equation work for any vehicle weight? And we can say right there that there's an issue. This is not going to work in the case of a vehicle weight of 0 pounds. Now that doesn't exactly answer the question of number 14. 14, it says, does this equation work for any vehicle weight? So we actually have to think of a vehicle's weight and decide, does this still work? So if we were to consider these possibilities, the 0 won't work because there's no vehicle that weighs 0 pounds. But is there a vehicle that weighs a certain amount of weight and that doesn't fit this trend, where it doesn't work? It doesn't fit this situation. So we can look at lightweight vehicles, we can look at heavy vehicles. And my first example, and the thing I went to and looked up was about semi-trucks. And it's not going to work for a semi-truck. And the reason it's not going to work is because a semi-truck, okay, the weight of a semi-truck is near like 12,000 pounds. And if I put in 12,000 pounds here, this equation is going to be at 0 or a negative number. And so that's not going to fit because a semi-truck still gets a certain number of miles per gallon. It might be small, but it's still going to be able to proceed and move forward and move a certain amount of distance on every gallon of gas.
All right, so moving on to our last example. The following table shows the largest vertical drops of 9 roller coasters in the US and the number of years after 1988 they were opened. So we're going to take this information, we're going to use that Desmos calculator one more time, and I'll walk you through that again. Okay, and we're going to enter the data into the table in Desmos. We're going to adjust our window using the smallest x and y values and the largest x and y values from the data. And then we're going to use the data to decide if it's linear or exponential. And we're going to describe how we know this is true. And then we're going to come up with our line of best fit and our correlation coefficient from that Desmos calculator. So I'm going to flip over to that Desmos calculator now.
Okay, so here we are again on the Desmos.com calculator. So the first thing we got to do is enter the information into our table. So we got to create a table. We got to go up to this plus sign in the top left, and we're going to click and then go down to table. And then we're going to put in the information from the table on the largest vertical drops in the years since 1988. And so that first one was a 1 year since 1988, and it was 150. And we're going to go ahead and hit tab, keep going and filling in that table. So you're going to pause the video, fill in the table, and then hit play once you've got it filled out. So go ahead and pause the video. Okay, so now that you have a table like the one I have here on the left, our table is complete. What we're going to do is we're going to make sure that we can see this on the coordinate plane. And so if we go up here into the top right, click on that wrench, we can change our scale. And so instead of going from -10 to 10 on the x-axis, I'm going to go from 0, seems like a reasonable, lowest value is 1, all the way up to 15. So I'm going to go up to probably something like 18, just to go a little bit more. Okay, we could go 20 maybe, just to kind of give us a little cushion. Then we're going to go for our heights, or the vertical drops of these roller coasters. And the smallest value is 150. So maybe 125 would be a good fit there. And then we could go up to the largest, which is 400, maybe go 425. And then we can see these points. So I'm going to move my person, my picture, I guess, and you can see now what's going on here. Now, if I go up here and I click and I say zoom square, what it does is it makes it square. It looks really weird, right? But we can also, it might help us in seeing what's going on here. Okay, so I want to go back out of this. Okay, and I'm just going to go back here and click on these. Let's see if that'll do it for me. Just wanted to show you that. And we're back. I had to go through and click all of those. I don't know if you saw that to help you see what's going on. But here we go. So now we have this, and you might think, oh, look, kind of little bow there. No, it doesn't really bow on this one. And we could look at two different situations, but we're just going to go ahead by starting and typing in our equation now. Okay. And to do this, it'll actually help us identify if this is linear or exponential. But remember, we're going to go y1, and then the similarity sign in the top left on your keyboard. Okay. And then you go m and x1, and then you got plus b. And you can see they're all pretty in line on this one, which is really, really nice. And we're just going to use that information that you can see in the left on number 2 for our line of best fit. And that's how we're going to use our Desmos calculator.
Now, we know that the data is linear, and the reason that we're saying that data is linear is because it's in a generally straight line, okay? And so since it's in generally straight lines, that means we're talking about a linear relationship. I mean, we could place our pencil over it like we talked about in the warm-up, but that data is in a generally straight line. So now in space 2, we already did this. We put the y1, the similar sign mx1 plus b, and hit enter so that we could come up with the information for our equation. And when we did this, we have to remember that we want to round our slope of y-intercepts to the nearest whole. And so we get the equation y equals, and now our slope was, what was it, 15.99, and if we round to the nearest whole, that would be 16, then times x, plus our y-intercept, which was 119.597, so we're going to go 120. And now that we have our equation, we look at the r value for our coefficient. Looking at r, it's 0.9358. And we want to round to the nearest hundredth. The nearest hundredth is 2 decimal places, so we're going to go 0.94. So what does this mean for our correlation? How would we describe this correlation? This would be a strong positive correlation because it's a positive value and it's between 1 and 0.8. So we have a few more questions. We're going to use a sentence. We're going to write a sentence explaining what the slope represents. Well, in this case, our slope is 16. And remember, if we write it as a fraction, it'll help us. So let's write it as 16 over 1. So 16 would be our change in y, which is going to be our feet in vertical drop. We're increasing 16 feet of vertical drop for every 1, and that's the number of years since 1988. And so we can say that our slope indicates that on average, because it's not every year that it's exactly the same, that's why our points weren't all on the same line, the vertical drop increases 16 feet per year. Okay, so number 22. If this trend continues, predict the vertical drop of the roller coaster built in 2014. So we have to think about how many years has it been from 1988 to 2014. So we could just subtract these two and figure out how many years that would be. If we subtract them, we would get that it's 26 years. And so that's the value of x. So this is going to be our x value. We're going to substitute it into our equation. So y equals 16 times 26 plus 120. And we would get that the drop, the vertical drop, would be about 536 feet in 2014. Now that we've reached 2004 or past 2014, we could go back to 2014 and see if there is a roller coaster that reached that vertical drop. And it may not be the case, but we could find out now and see if this equation still is true. Okay, number 23. Write a sentence explaining what the y-intercept represents. Well, remember, the y-intercept is just a point. It's the point 0, 120. So if we're looking at this point, we have to think about this as time. Our time is 0 years. But remember, the context of our situation is 0 years from 1988, which means we are talking about the year 1988. The 120 is talking about the vertical drop of a roller coaster. So we could say that in 1988, the greatest vertical drop was 120 feet. Okay. Number 24. For how many years after 1988 do you feel the equation is valid? And to decide this, we have to think about what is a possible vertical drop that a roller coaster could have. Could it actually go 536 feet, vertical feet of drop? Or is that going to be a situation where it's unsafe and they are unable to build that kind of a roller coaster? And so we would have to do a little research to decide this. It's a very open-ended question, and it's what do you think? So take a minute and maybe look something up or think about this. When would this stop being valid?
This concludes the video for Lesson 5-2 for Secondary 1 Math, Scatter Plots.